Hello YouTube, this is Eric from Coder Snacks. Today, we're going to talk about the three-sum problem. Given a list of elements in a target, find some triplet that adds to the target. Let's get started. I've been seeing this problem in a variety of places recently, and it's interesting to see some of the tools you can use to improve a solution from brute force to more optimized. It's also interesting to see how having a variant of a question can dramatically change how we approach it. Questions you can ask for this problem are similar to last time. What size list should we plan for? What is the range of items? Does it include negative numbers? Should we return one solution or all solutions? And can we use elements more than once? For our purposes, we'll assume that our list is no more than medium-sized, maybe thousands of elements, and our items are integers, positive and negative. We'll return any single solution, and we can only use an element once. Since we've recently studied subset sum, it's tempting to look at this problem and conclude it's the same. However, using three elements changes the problem significantly. First, it's no longer exponential time. Let's look at a brute force solution. In this code, we look at every triplet of items and check if they equal our target. If they do equal our target, return that solution. Some simple tests seem to work, but this code is wrong. There's a bug in this simple solution. Can you find it? If you'd like, pause the video and give it a shot. The problem is that A, B, and C could all be the same value, but we can only use each element once. For example, if we have the array 4, 5, 6 and a target of 12, there shouldn't be any solution, but this code returns 4, 4, 4. We could fix this by continuing if two of the indices are the same, but there's a simple way that's more efficient. In addition to the bug, we're doing a lot of duplicate work. For example, if A equals 4, B equals 5, and C equals 6, that's the same triplet as A equals 6, B equals 5, and C equals 4. We're checking each triplet 6 times. To fix this, we'll use list indices and decide that our indices will be in ascending order. To do that, we'll start the J loop at I+1 and the K loop at J+1. This also ensures that we're not trying to use the same element multiple times in the same solution. We run our code on our sample, bug fixed. Starting a loop after the index of a previous loop is a common efficiency trick you should keep in mind. For a touch of added efficiency in our brute force solution, we can stop the I loop 2 before the end. We need two numbers for J and K after all. This doesn't really gain much because the J and K loops would just fail immediately anyway, but it's a nice touch. Our current code runs in O of n cubed time. How can we improve this? Let's briefly look at a simpler version of this problem called Twosome, where we use two elements instead of three. How can we solve this? A first solution is to look at every pair of elements as we did for triplets. This takes O of n squared time. Can we do better? What if we sort the array first? This takes O of n log n time, but does it help us? Let's look at an example. Once we sort the array, we can look for pairs from both ends. Take the largest and smallest numbers, 20 and 1. We add them and we get 21, which is greater than our target number. How do we make our sum smaller? We make the larger number on the right smaller by moving it left. Now we have 1 plus 18, which is smaller than our target, and we make the smaller number larger. 3 plus 18 is 21, and we move 18 in. 3 plus 13 is 16, and we move 3. 6 plus 13 is 19, we move the 6. 7 plus 13 is 20, which is our target, and we return the 7, 13 pair. If we were looking for a pair and the numbers met in the middle, we'd return no solution. Scanning from both ends takes O of n in the worst case, but the sorting was O of n log n, which is larger, making our runtime O of n log n. Can we do better? What if we put the numbers into a set? That takes O of n. Once we do that, we look at each element of the list and see if its complement is in our set. Here's an example with a different target. We see the number 7 and check if 24 minus 7, or 17, is in the set. It's not, so we continue. With 8, we check for 24 minus 8, or 16. Also not in there. 24 minus 13 is 11. Is 11 there? Yes, we can return 13 and 11. But be careful, this has the same bug as before. If we change our example to contain a 12, we could return 12 plus 12. To fix this, we could use a hash table or collections.counter and store how many times each number appears. If it's more than once, we can use it a second time. Since looking up an element in a hash table is O of 1, doing it n times makes this algorithm O of n. Now that we have an O of n solution for the twosome problem, can we apply either of these techniques to the threesome problem? Let's try the hash table solution first. We can use the same method as twosome, but with pairs of numbers. Let's loop over the pairs of numbers and see if the third number, which will be the target minus the sum of the pair, is in our hash table. We can store the indices to make sure we're not getting duplicates. Let's write some code for this. We start by making a dictionary, number table, that stores for each number the list of indices where we can find that number. We need this so that we don't use the same element twice. Then, we loop over each pair of numbers and make a partial target of our target minus those two numbers. Then we look in our number table at all the indices for our partial target. For each of those indices, we see if I, j, and k are all different, and if they are, we return that solution. If we go all the way through without finding a triple, we return none. Since the index duplication thing looks a little complex, we also want to add a few more tests making sure that it works okay. We run it, and it seems fine. What is the runtime complexity of this code? Putting the elements into the table is O of n, but that set of I, j, and k loops looks like O of n cubed, doesn't it? I and j are both O of n, and maybe if all the numbers are the same, k could be O of n too, right? Thankfully, no. In the worst case, we check 3 numbers in the k loop, and everything in the loop is constant time, so the k loop is O of 1. For example, if all the numbers are the same, at worst we could check that a k is equal to an I, and a k is equal to a j, but after that, k has to be different. Therefore, the runtime complexity is O of n squared, and we use O of n space to make the number table. This feels a bit messy, and we'd like to use less space. Can we do better? What if we use the other twosome approach, where we scan in from both sides? The question is, how do we adapt our twosome approach for 3 elements? Imagine we already have a function to do twosome scanning. First, we sort the list. If we assume we're using the first element, we can use this function to check the rest of the list for the remaining sum. Here we assume we're using the 1, and then we check if we have a pair that adds up to 19 using our twosome function for the rest of the list. There is, and we can return it. Let's try with a different target. This time when we look for our partial target, we don't find one. So we'll try starting with the next number instead. Notice we don't have to check the 1 anymore. If there were a triple with that 1, we would have found it last time. We look for a pair that adds up to 30, and we don't find one. Next we try with 6, and we find 7 and 20, which we can return. What's the time complexity of this? We use all the elements for the first element, which is O of n, and for each of those first elements, we do an O of n scan through the rest, making this O of n squared, and O of 1 space assuming our sort is in place. If we can't do an in-place sort, this will take O of n space for the sorted array. Let's write the code to do this. We'll sort our numbers, and then loop through all the first elements. We calculate the partial target that the other 2 numbers need to hit, and initialize the indices for the second and third element. Then, as long as our third element is after our second element, we check the partial sum for the second and third element and compare it to the target. If it's the same, we can return a solution. If it's too big, we make the larger element smaller, and if it's too small, we make the smaller element bigger. At the end, if we didn't find any solution, we return none. We add a few more test cases to check whether or not we have any off by 1 errors, but everything looks pretty good. It's interesting to note that sorting, while worse in the twosome version, is just as good for threesome. The difference is, in the twosome version, n log n was bigger than the rest of the algorithm, but here it isn't. The rest is n squared. If you have an algorithm with a larger time complexity, sometimes it's a good idea to see if sorting helps you out. Whether there is a better than O of n squared solution is an open problem in computer science. There are some specialized solutions that are better given various constraints, but O of n squared is the best known solution in the general case. I'll put some links in the description. Alright, enough. Twosome, threesome, subset sum, enough summing. Let's look at something else. Next time, we'll look at our first tree problem. Write a function that takes an in-order traversal of a binary tree and a pre-order traversal of the same tree and reconstructs the tree itself. Don't know what a traversal is? We'll explain in detail in our next video. Speaking of which, I hope you got something out of this video. If you have any questions, comments, something I've missed, or problems you want answered or covered, let me know in the comment section below. And if you enjoyed this video and want to see more, it would be great if you liked the video, subscribed, or both. I really appreciate it. See you here next time on Coder Snacks.